We've already made a lot of progress getting our int vector class to behave just like an actual vector of ints. So we've already written push back, we've got .at, we've got .size, we've proven that we have the ability to iterate over the vector, at least using indices for now. We've solved the problem of passing the vector by constant reference to a function, but the problem is the vector still doesn't have that classic behavior of appearing to be able to grow and shrink as needed. I'm still not able to add just as many elements as I want. And that's because earlier, as a simplification, just to get one thing done at a time, we've initialized the vector to have a storage array of a fixed capacity. So it's a storage array, in this case, with capacity 10. And that means that as soon as I push the 11th element, I am in trouble because our array will be exhausted, and we currently have no facility to change its size. And really what the vector is doing for us, the reason we like using vectors so much, isn't all of these functions, because we can do the equivalent thing with a C-style array. It's the ability for the vector to know its size, tell us its size, and for the size to change as we need it to, so as the vector grows and shrinks. And so I'm going to run the code that I have here, which shows off this attempt to push a whole bunch of numbers into the vector beyond its natural capacity. So I create an empty vector, I then try and push in 1,000 elements, so the integers 1 through 1,000, and then, assuming that that operation succeeds, I go through it again to prove that they're all there, and I add them up. A note to make for later is that the sum of the numbers 1 through 1,000 is this number. So when I finally get it working, I expect the sum to be this. Okay, so let's try running the code as it's currently written, using the vector class that we wrote in the previous video as our starting point. And if I do this, I get this logic error. I'm told, sorry, you can't use pushback to add more than 10 elements to the vector because the vector doesn't have that functionality. And I pointed out earlier that I like using the logic error class here because it's not just telling the programmer that something unexpected happened, it's telling them that they shouldn't have written code like this to begin with. So not that they've missed an error case, but that they should know better than to call pushback on a vector that can only ever hold 10 things. We would like to remove that limitation. We would like to make it so the vector can resize itself as needed. And the first thing we should understand here is that there's no such thing as a resizable array. Deep down, the vector is storing all of its elements in an old-fashioned C-style array. All I want to do is to use the power of abstraction and encapsulation to make it look to the outside world as if the vector is one of these magical unicorns that can grow, that can resize itself as you add more elements. And I guess if I remove elements, it can also shrink itself. The way I'm going to do that, though, is suppose that my internal storage array had size 3, and it fills up. So I have this vector 6, 10, 17, and I would like to add a 4th element. Well, we know that C-style arrays have a fixed size. I cannot make them any bigger than they already are. What I can do, though, using dynamic allocation, is I can observe this array here was dynamically allocated. I can dispose of it whenever I want. So if I want to produce the effect that my vector is resizable, what I could do is make a brand new array that's bigger, copy in those 3 elements, then I can dispose of the old storage array and just pretend that all along this was my storage array. If I do that seamlessly and I encapsulate it, nobody looking in from the outside would be able to tell the difference. So whenever they try to add the 4th element, I just suddenly do an internal resize operation, and when I'm done, there is space for a 4th element, and I can add the 4th element. So from the outside, it appears as if the pushback operation succeeded and the array magically resized. But really what I was doing all along was just juggling arrays. I don't resize my original storage array, I just make a new one and pretend that that was there all along. And that's going to be my goal. I would like to create some functionality in my vector type so that if I need to change the underlying size of my storage array, I can do that apparently from the point of view of the outside world seamlessly. Okay, so the first thing I want to do is skim over where I'll need to do that. So I'm still going to initialize my vector to have an internal array of size 10. And the idea will be when I try to actually add an element beyond that capacity, then I have to worry about it. If my vector has an internal capacity of size 10, but I only ever add 5 elements, nobody will care. There's no need to resize. So when will I need to resize? I would argue that I only ever really need to resize when I add an element and maybe when I remove an element. So if I add an element and the internal capacity is exhausted, that would be line 50, then obviously I have to resize to produce the effect that I can add as many elements as I want. When I remove an element, obviously I'm never going to have I'm going to leave in this exception here, so I'm never going to allow the vector to go down below 0 elements, obviously. When I remove an element, I suppose there is the chance that my internal array ends up being so big that I'm wasting space. For example, if I keep removing elements, and my internal array has size 100, and I end up with 4 elements in my vector, maybe I ought to downsize. Maybe I don't need all that extra space being wasted. So I suppose it's worth resizing in cases where the number of elements in the vector is so much smaller than the capacity of the array that I don't need such a big array anymore. To avoid having to debate exactly when that should happen, I've built into the prompt a decision on that. So we want to resize the underlying storage array. If I'm adding elements, when the array fills up, I will double its capacity. And there are reasons for this. There are reasons I'm not just adding 5 to its capacity, and that's because it turns out I want to reduce the number of resize operations that I do, and for reasons that might become clear to you in a higher level course, doubling the capacity will result in a very fast vector when I'm done. The number of resizes is going to be very small if I just keep doubling it. As far as shrinking the capacity, whenever the number of elements actually in the vector drops below 25% of its capacity, then I reduce the capacity by half. So for example, if I have 100, if my underlying array has size 100, and my vector drops down to having 24 elements, then it will resize the storage array to have size 50. I'm still going to leave in a cushion of extra space because I know that I want to avoid resizing if I can. So if there are only 24 things in the vector, I'm not going to resize the vector to be size 24. I'm going to resize the storage array to have size 50 so that there still is some extra space in case you want to add more elements later. I should observe, though, that the operation of resizing isn't specific to adding elements or removing them. I may want to do the same type of operation, which is to swap storage arrays when I'm adding something in pushback and when I'm removing something in popback. And if I were to extend this example further and add functions like .insert, I might want to do resizing in a lot of different contexts. That's a hint to me that I don't want to write all of the resizing logic inside of pushback. Because if I do that, I'll have to duplicate it inside of popback or inside of insert later. Instead, the way I'm going to tackle this is I'm going to add an extra function, a member function that does the resizing for me. And then I can just call it whenever I need it. Because it shouldn't be the outside world's problem when I resize the underlying storage array because of the encapsulation I'm trying to achieve, under this encapsulated setting, I don't think anybody outside the vector class should even know that the resizing is happening. Therefore, if I write a function to do my resizing, I want that function to be hidden from the outside world. And that is why I'm going to write my resize function as a private member function. We haven't seen too many of those so far. I think this is a great example of a place to use a private member function. So what I'll do is I'll write this function called resize, and it takes the new capacity, which could be larger or smaller than the existing capacity. So for example, if my vector has a current capacity of 50, I might be doubling it and give a new capacity of 100. On the other hand, if my vector has a capacity of 100 and I've decided to downsize, I might want a new capacity of 50. So the new capacity could be smaller than the existing capacity, and that should be no problem. What would be a problem is if the new capacity is not big enough to store the number of elements in the vector. The capacity of the vector doesn't necessarily tell us its size. A vector with capacity 100 might only have 5 elements in it. So I could easily change my capacity from 100 to 25. The problem is, if I'm downsizing, I want to make sure the new capacity of the vector is at least big enough for the number of elements that are actually in the vector. Not the current capacity, the number of elements that are actually stored in the vector, the active size of the vector. So if you try and resize, keeping in mind you can only do a resize operation from inside the class, if you try and resize and you give me a capacity that I can't work with, then we've got a problem. I think this is another setting, a good setting for a logic error. You, the programmer of the vector type, should know better than to do a resize that results in the vector being smaller than the number of elements it can contain. So I'm going to say invalid resize operation. All right, so the idea there is that if you ever get a logic error in a program, it is definitely not an omission, it is a programming error. You have actively done something wrong as the programmer. Whereas a runtime error might just be, hey, something you weren't expecting as the programmer happened, maybe you should now add some logic for it. Or the program simply can't continue because of something so bizarre that you, the programmer, should never have expected it, and the program now has to end. But here a logic error says you shouldn't have been calling resize in this case. You shouldn't have been giving an invalid capacity. If we get down to line 73, that means that no matter what our new capacity is, there will be enough space in our new storage array to store all of the elements. And so all I have to do now is make a new storage array and then copy all of the existing elements into it. So I'll make the array called new storage. And it will be a new integer array of the size of the new capacity. And now what I want to do is copy every element of my vector into the new storage array. So I'll say something like this. I'll start by unsigned int I, start that at 0. I'm just going to copy all of the elements of the vector. So not up to the current capacity, because not every element might be used, but instead up to the current size of the vector. And I could call the member function here, or I could just use vector size directly. All right, so what I'll do is I will copy into new storage at index I. I will copy the value at the current storage array at index I. When I'm done all of this, the new storage array will now contain every element of my vector. And so all that remains is to make sure that I dispose of the old storage array and to set the new storage array to be my real storage array. So eventually I'm going to want to run this. This is saying I'm going to set the storage array for the vector to be the newly created array. Now, before I do this, I need to be careful, because remember that our pointer storage in the class, we are representing our storage array by a pointer to the beginning of an array. It's a C-style array, so we should be familiar with that. And currently, we've got this storage array that goes off into the distance, and I've just made a new one. And my goal, because obviously the new storage array is reflective of the capacity that I want, is for when this function ends, if I use the storage array for the vector, it to be the new array. So once the function call is over, to any outside observer, it looks as if the vector storage array was always the new size that I wanted. There's no real difference between this old array and new array. In fact, to an outside observer, there is no new array. There was the array that was there all along. The issue is this old array needs to be destroyed. I allocated it with new. I need to delete it with the delete operator. I have to do that before I redirect the pointer. So I'm going to follow this protocol here. I've got my storage pointer. It points at my old storage array. I will then delete the old storage array. Okay, now I should understand, after line 77, the storage pointer is now invalid. But on line 78, the very next line, so what I've just done is destroyed my old storage array. I will then redirect the storage pointer, the class member called storage, to point at my new array. And that means as of the end of line 78, as far as anybody is concerned, my storage array is now valid again. And because I copied every element into it, nobody could really tell the difference. Nobody could tell that this is actually not the same array that was there before. Okay, so I've got that. There is my resize function. So I now have implemented this big abstraction of having a resizable array, when really what I'm doing is just juggling different arrays. I'm actually creating new arrays and then putting them in the place of the old array. Now what I need to do is use the resize function where necessary. So I need to perform the resize operations dictated by the prompt up at the top. When the array fills up, so if I have a capacity 10 and you try and add the 11th element, then I need to resize the array. I need to double the capacity. On the other hand, if the size of the vector drops below 25% of its capacity, I need to shrink the underlying storage array. So we'll start with the case where the vector fills up. So if you do a pushback operation and the current size equals the capacity, that means every available spot is full. There's no point in resizing until then, until after the vector is already full, and then I try and add one more thing. It's at this point that the vector would overflow. So here is where I would do the resize operation. So I call resize, and then I pass in the new capacity as capacity times 2. And actually, I just realized I did forget one line in my resize function. So I'm going to go back down and add that, which is what I have to do is, of course, change the capacity that's been stored in my object to reflect the new capacity. Because I just added this new storage array, I need to make sure that the capacity variable keeps up with that. So set to equal the capacity of the new storage array. And the idea here is at any given point, storage is the pointer to the beginning of an array, and the variable capacity, the class member capacity, is the number of elements available in that storage array. Obviously, as time goes by, I need to keep that up to date, because I need to know when it's time to resize again. Okay, so I think the resize function is now complete. Okay, so what I do is I call the resize function in pushback if the size of the vector before I've added the new element is equal to its capacity. That means I need to resize. So I call the resize function. That just takes care of everything for me. Now, the one thing this example is sort of not getting at is, I suppose there are cases where a resize operation may fail. So an example being, what if there is not enough memory available to make the new storage array? That is one place where we're doing a simplification. The new operator could throw an exception if it's unable to do what you want. I would argue that for our purposes, if it does that, we're sort of out of luck, and therefore the program may just have to crash. That is something that the actual vector type might have to handle in a bit more of an elegant way, although arguably, if the vector can't resize itself, it just can't do its job. That's a pretty fatal error in almost every case. But I will put a note here that we're not really consciously handling that. Okay, so the vector size equals the capacity, do a resize operation. When the resize function finishes, as far as we're concerned, the storage array now has extra space, and we can perform our pushback operation as we normally would. What about in pop back? So in pop back, what I'm doing is I'm removing an element, and we heard in part 1 that removing an element is sort of a fictitious operation, because all we do is tell the outside world that the vector size has decreased, and from their point of view, now there are fewer elements in the vector. After I'm done this pop operation, maybe I discover that the vector size that's what I'm left with is less than 1/4, so below 25% of the capacity of my storage array. And if that's the case, then I want to resize the storage array. I want to downsize a bit so I don't have too much wasted space in my storage array. As per the prompt at the top, if the size drops below 25% of the capacity, set the capacity to 50% of its current value. So don't clamp down tightly on the storage array. Leave a few extra elements because we like having extra elements in case somebody uses pushback. But don't allow the array to become, egregiously empty. Get it to a point where the number of empty spaces is somehow in proportion to the number of elements. I'm going to add one more check here, which is I don't want to fiddle around too much with tiny arrays. So if the capacity is less than or equal to 10, then I don't want to resize further. So I don't care how few elements the vector has. If the capacity is equal to 10, just leave it, or if the capacity is less than 10. If the capacity is greater than 10, so if the capacity is 20, then we can downsize. But at some point we want to stop downsizing because if my vector has only one element, I don't want to worry about a capacity of 2 or something. I will allow my vector to have a minimum capacity of 10 elements. Okay, so I think these two checks implement that. The vector can grow as needed, and then as it shrinks, the capacity shrinks as needed down to, I think, a reasonable minimum of 10 elements. And so we'll try compiling that. And I should add, as you noticed, there was an omission that I made when I was writing resize. This type of thing, this is actually a pretty touchy operation. It's pretty easy to make mistakes here. There's also the compiler giving me a warning about something. On line 73, it's saying my new capacity is an int. Shouldn't it be an unsigned int? And I agree. We're using unsigned int for all of our other indices and capacities. We should use unsigned int for resize. All right, there we go. It compiled, and let's see what happens if I run it. Notice how here, first off, that was pretty fast. We didn't see any visible delays. And in main, I was able to use pushback to add all 1,000 elements to my vector. Now again, in the interest of making this a more compelling watch, I haven't added any more tedious testing, but you could do that. You could even add print statements during resize operations to verify that they are indeed happening. I believe that they are happening because I was able to use pushback to add 1,000 elements, the numbers 1 through 1,000, and once I go through again and add them all up to prove that they're all there, I get this. And as I mentioned at the very beginning, that is in fact the sum of the integers 1 through 1,000, something you could check in a variety of other ways to verify it. So I think right now this is evidence that my resize operation is working. You might look at the posted version of the code and do a few more tests to verify that I'm not lying about that. So what happens with the shrinking case? We haven't actually tested pop back here. And one of the reasons why it's hard to do that in main is because of the encapsulation. I'm not supposed to know as an outside user of the class that any resizing is happening. So it's very hard for me to prove that the resizing is happening in the way I want it to. I can definitely prove it's happening because I was able to add 1,000 elements, but it's sort of hard to prove that it's happening exactly how I want it to and at every point that I want it to. And that's something that normally you would do more testing of. For our purposes, for the sake of solving the task on a video that maybe people actually want to watch, I haven't done any more testing. But if you do assignments or something, you probably want a bit more fine-grained testing than this. In any case, I now have a vector type that is able to behave like a vector we've been using all along. We have almost every operation that we've seen, let's say over weeks 1 through 3 of this course, working with vectors. The things that are missing are the ability to use iterators, which deep down also connotes the ability to run for each loops, and the ability to make vectors of literally any type. And so we've got a couple of other loose ends to tie up in the meantime, one of which is how do I initialize a vector with a bunch of elements already in it? And also, how do I make copies of vectors efficiently? That's something that we're going to have to work on that's going to involve a copy constructor. We're going to talk about those things over the next two videos. Then we're going to talk about how do we implement a class that has an iterator? How do we implement a custom iterator for our vector type?